So the peer prediction lectures were supposed to be given by YUQIN. Unfortunately, she was unable to travel here to be with us. And so her amazing students who are here somewhere, up here, great, Yongkang and Zihuan. And YUQIN prepared these slides, which Bo and I will be going over today. Fortunately, we have experts here on hand to help us if we get stuck. YUQIN is a faculty member at the Peking University in China. She's one of the pioneers of designing good mechanisms for this area of what's called peer prediction. So I was really looking forward to having her here so that you guys could learn from the expert in this area. Her PhD is from University of Michigan, working with Grant Schoenbeck, and she's been, I think, at Peking University for about 6 years. For a number of years, I've been fortunate enough to get good advice for her on, how to think about these peer prediction mechanisms, and also she has, been supervising some of the very strongest students in China, and so getting a chance to work with them has always been fantastic. And so it's great that we have a couple of them here. So with that, so our strategy today is we're gonna go over her slides, but some of the proofs are a little bit high level in the slides, and so we thought we'd, following the tradition of the past lectures, go into some more details of the proofs on the whiteboard. Again, so bear with us a little bit. This wasn't sort of the planned approach to teaching this stuff. And maybe you'll help us puzzle through some stuff we get confused about. I'm looking forward to learning this material really well with you all at the same time. Cool, so the plan is to start by discussing this original peer prediction mechanism. So peer prediction basically, before we jump in, peer prediction addresses one of the questions we got yesterday, which is these scoring rules we were talking about yesterday rely on having ground truth. And so you have to compare the prediction to some objective truth to be able to then incentivize the forecaster to report what they think about the truth. There are many, many scenarios where we don't have ground truth. One of the canonical scenarios where we don't have ground truth is, for the last decade, researchers doing machine learning have been trying to collect labels for things like images, where you want to develop algorithms for labeling the images, but you need then to know the ground truth label for the image. And how do you know the ground truth label for the image? Well, maybe we just collect a bunch of images and we try to ask people on the internet to label these images for us. We pay them a little bit, but we didn't know the ground truth in the first place. So how are we gonna be convinced these labels are correct? And so that's sort of one of the initial applications of peer prediction that got people thinking about it. YUQIN has been, I think, really a visionary in advancing the kinds of applications we think about using peer prediction for. And amongst other areas, you might, amongst other applications, it might be that you don't have access to ground truth and that's why you're doing peer prediction, or it might be that just isn't ground truth. Maybe you want to solicit people's opinions. Okay, and if you want to solicit people's opinions, what are the ground truth anyway? Right, that's what's in their brains. And so they're the only one who has access to that. And so how can we as a principal come up with a scoring rule, right, that gets them to say what they truly think about something? And so that's another area where we're not likely to have ground truth. And so for like psychological surveys or other kind of surveys, we might want to actually know what people believe. And so, there have been, examples where we would have wished we'd had much better statistical information. You can look at some US elections where the polls were really off. You're like, why did we not know this answer from the polls? And it's like, well, probably that information was out there, but we weren't eliciting it in the right way to get people's actual true opinions or what they knew. And so there are a number of opportunities for developing elicitation mechanisms in scenarios where you don't have ground truth, and that's what today's about. So we're going to start with this original mechanism. This mechanism actually, it was when the economics and computation community first instantiated their Test of Time Award, which awards papers over 10 years old. This was the first paper to win that award. And so we're going to see the details of that first. Then we're going to talk about sort of extensions of that, trying to remove some of its limitations and some of its assumptions. Then we'll have a review of information theory, and then talk about sort of the latest and greatest work, which is work by YUQIN and her collaborators on basically removing all of the assumptions. Okay, all of the assumptions that seem problematic for making these things work. Okay, so that's our plan for today. Cool. So just a reminder from yesterday, and one of the things we did last night was try to get the notation in YUQIN slides to match more than the notation we used yesterday, which is going to be the same as the notation that Bo's going to use tomorrow. So that'll hopefully be easier for us. So a scoring rule takes a report and the realized state, right? This is if you know the ground truth state. So R is the report, distribution of our outcomes, Y is the realized state. And it's proper if we try to maximize our report in expectation over our true belief P, right, of the score that we get, then the true belief is in the maximum. So just reporting our true belief is a good strategy for us. Okay, and then as I said, and as someone asked yesterday, scoring rules require knowing the ground truth. There's no way I can implement this function S of Ry without knowing Y. Cool, so this image showed up on the internet a while back and confused the heck out of people, because some people look at this and see white and gold, and some people look at it and see blue and black. So this is an example of a situation where subjectively, like what's in our heads is different for different people, and there isn't a ground truth. It's not like, I mean, there is a ground truth, it's what's in your head, right? But there's no way that, we as a principal could elicit that information knowing what's in your head. Okay, so let's think about how we might try to elicit this information from people truthfully and reward them truthfully for their information. Okay, why does this keep advancing? Okay, so this is the challenge. Yeah, this is the challenge. And so what is a peer prediction mechanism going to look like? So we imagine we have a lot of, we'll call peers. Okay, so again, so in scoring rules, we had just one agent. In peer prediction, we're going to have many agents. So like maybe all of you in this room are going to participate in this mechanism shortly. So you're all going to make a report. You're going to say it's, what are the colors? White and gold, or blue and black. Okay, that's what you're going to say. And then, so you report this Ri, the other agent is going to report, and this notation R minus I just means everyone but. Does anyone know how to make it not advanced?
That's the screen, it will move also. You can work here. If you work here, then it will be fine. This screen is
all right, I don't know how to present slides.
you can see it.
Okay, and so then.
If you sleep, at least. Lose your pyjama.
I'm glad the heckling has started already. Okay, so you as an agent I make your report, the other agents make their report, and then, kind of like we did before, we have a decision problem. Where we're going to evaluate your report against, some other stuff we know, which is the other agent's reports. I'm going to click it once. Okay, so here is a way to start thinking about how we might do this. Let's suppose everyone is reporting. So let's ask the question differently. What if instead of asking you what you think, I'm going to ask you what you think your friend thinks? Okay, and so your friend's report is kind of like the state. Okay, the friend either thinks it's one of the color combinations or the other color combination, and I want you to report the probability that your friend thinks it's one of the color combinations. Okay, so we have this photo of the dress, you and your friend are playing. I want you to guess the probability, a number between 0 and 1, that your friend will see the dress as white and gold. That was one of the combinations. Okay? And then your friend will reveal how they see the dress. Okay? And so this is a setting where, if your friend truthfully reveals, right, we can just apply scoring rules because now we know you're predicting your friends and your friend truthfully reveals, and so maybe this is going to work. And here we've written down basically the quadratic scoring rule, right? 1 minus p, which is the quadratic scoring rule in the case that you said white and gold, and 1 minus p squared, so this is plugging in 0 for the truth in the case where your friend said blue and black. Yes, please.
Me and my friend, we don't talk.
That's correct. Your friend across the room. Okay. So how might you think about that? So let's try to put it back into our decision theory framework that we had from yesterday. And so maybe there's a joint distribution over what you see. And maybe it looks like this. And maybe everyone knows this. Okay, so again, here are these probabilities. They sum to 1. And so 0.4 is the probability you both see white and gold. 0.4 is the probability you both see blue and black. 0.1 is the probability you both see, one of you see white and gold and your friend sees blue and black, right? Etc. And so if you see white and gold, you can Bayesian update and get a posterior belief on what your friend sees, right? Because you're in this row, so you divide by the total probability of this row, right? And you get 0.8 and 0.2, because the row probability is 0.5. And so your posterior belief, given that you see white and gold, is the probability that your friend sees white and gold, conditioned on the probability you see white and gold, and that's 0.8. Okay, and the posterior belief, given that you see blue and black, which is the probability your friend sees white and gold, is 0.02. So if we're in this row, your probability of white and gold will be 0.2. Cool. So let's imagine that the mechanism designer also knows this information. Okay, then we can design a mechanism for asking you your belief, your signal, right? So I'm going to ask you, what do you see, white or gold or blue and black? Okay, you say white and gold. Now I know your posterior, so I can map your report through this posterior oracle, which tells me what I think your friend sees. And then you can say, oh, if you see white and gold, the posterior oracle, we say your friend has a probability 80% of seeing white and gold. Okay, and then we can put that in the scoring rule we had before, which was a proper scoring rule for predicting your friend's belief. Okay, so I use the fact that I know the joint distribution over your signals to take your signal and infer your belief on your friend from that. And then I can play your belief in the proper scoring rule for beliefs to predict your friend's report. Okay, and this, is that kind of clear what's happening? So the algorithm is ask for reports. Use our knowledge of the pi, the joint distribution on signals, to infer posterior beliefs that each person would have on the other person, conditioned on, assuming that the signal they report is the true signal, right? And then take those posterior beliefs, put them into the proper scoring rule for beliefs to predict your friend's signal. And that's what it says here. Perfect. Okay, so again, in this description of the game, the I is like the mechanism. So you and your friend are going to play. You report white or black, or you each independently report white or gold or blue or black. And then if you say white or gold, we're going to play the proper scoring rule to predict your friend's report using 80%. And if you say blue and black, we're going to play that using 20% because we know this payoff table, the prior, okay? And then we give you the payoff of that scoring rule of how well your posterior that we calculated predict your friend's signal, which is whether they saw, which color they saw. Cool. So, yes, please.
The person playing this game, doesn't their best action depend on their belief about the joint distribution, or is the true joint distribution known to everyone?
Yeah, exactly. Great question. The true joint distribution is going to be known to everybody. So we're going to assume what's very typical in economic theory, which is there's a common prior. The common prior is the joint distribution over the signals we receive. And we're going to design a mechanism that knows the prior, so the mechanism can implement this posterior oracle of mapping signals to posterior beliefs, okay? And both the players, when they choose what to do, they're going to choose what to do also knowing and agreeing of this distributional information. Cool, so I want to talk about what equilibria are here. Again, we're playing a game with two players. We want to know what both of them are going to do. We're going to look at equilibria. Okay, so a strategy is a mapping from the, this should have been X, sorry, the state X, the signal X that someone receives to a distribution over reports they're allowed to make. The reports are either reporting one color combination or the other color combination, so they can randomize over those if they want. Okay, and a strategy profiles an equilibrium if each player is happy following the strategy profile over picking some other strategy, and this is player one, changing their strategy to this other strategy. Okay, and this is player two's equilibrium condition as well. Okay, and then the main result from this award-winning paper, Miller, Resnick, and Zeckhauser from '04, is that truth telling is an equilibrium in the posterior oral peer prediction mechanism. Okay, so everyone telling the truth, revealing actually what they believe, is in equilibrium. And so why is that? So let's assume agent 2 is reporting the truth. They're reporting X2, what they truly see the colors as. Okay, so on signal X1, our true belief on X2 is Q of X1, the posterior that we had from the table, right? That's our true belief on X1. Okay, and we know our payoffs are going to come from the scoring rule, where our best strategy in the scoring rule is to have our true belief input. So the way to make that happen is to report X1. So X1 would be my best response. If I report the opposite of X1, the opposite color, then I'm putting in a different posterior, which is not the posterior that optimizes, not my true belief. And so it's the wrong number, so it's not a good thing to input. Is that clear? Cool. So this was 20 years ago that they wrote this paper. And lots and lots and lots of awesome stuff has happened since then. And so the slides hopefully have been sent to you. And so you've got a lot of the references for all the great work that's been following up these initial papers. And so we won't talk about it that much, but we'll introduce some of the sort of highlight ideas as we go through the presentation of the great work that followed. Okay, so up next is this talking about the single question mechanisms, and we'll talk about what's called the Bayesian truth serum. Yes, please.
Why, is it because of insensitivity that we don't ask the people to report directly the state and use it directly, or because you could always ask like they want to tell the data in their own state, and then use it instead of like
Yeah, we'll get into some. So I think what you're asking is, actually, I'm not quite sure what you're asking. So so we are directly asking them what they think the color is, but then we're using our knowledge of the joint distributions of what people think the colors are to figure out what we think their belief on the other person is, and then use that in a scoring rule. So that's what we're doing. So you might think that, well, why don't we just ask people what they think the colors are and reward them if they agree? We'll talk a little bit about this in a little bit, right? So if you both say the same thing, you win. If you say different things, you lose. And if we're asking you to label images like dogs and cats, maybe output agreement is good enough. Here's what goes wrong with output agreement. What if I'm asking you to label dogs and cats, but it's noisy, you can't really see some of the pictures, right? But you know that they're just, 100 times more dog pictures than there are cats pictures. So if you can't see something, we should just say dog. Right now you ignore what you think it is. You squint, you think it's a cat, but you can't really see it, so you should just say dog, because there's so much more in the distribution. And so the point is, mechanisms that don't take into account the prior are going to make they're going to have these incentives of basically, going with the prior instead of going with what you see. And so we really want to avoid that kind of a thing happening.
I guess another question is, if you have the prior, what do you need in a large
That's a great point. And so the whole outline, basically, our goal here is to remove the heroic assumptions as we go down, to start here where we assumed we knew the prior. If you know the prior, why are you even asking these questions? Well, maybe we didn't want to know the prior, but we wanted to know what actually people thought about individual images. So maybe we know the prior over how people see dogs and cats, but we don't know whether this image is a dog or a cat. So it's still useful even if we have to know the prior, right? But what you're saying is like, for this question of red and blue, if maybe I was asking this question because I want to know, what does the general population think about how many people see red and how many people see not red, but blue? Geez, one color combination and the other color combination, right? I want to know that. Okay, and the point, if I know the prior, then I already know this. Yes, please.
In the last game, is it true that the only equilibrium is the truth-telling one, or I can have this equilibrium where we both say the same?
So the question was about whether this was the only equilibrium, or were there other equilibria. And what we'll see, actually, all of these mechanisms have multiple equilibria. In particular, there's a particular kind of strategy called a permutation strategy, where we just decide to speak a different language. And so we map, the word dog to the word cat, and the word cat to the word dog, right? And that's going to be an equilibria as well. Right, and so you can never get rid of those strategies, but if we assume people are sort of speaking the same language, maybe we aren't so worried about those strategies. It's much more easy for people to see a dog and say dog than it is for people to say dog, look up in their dictionary of how we're swapping the words around.
Can they coordinate? That's what I was trying to say. Like, the mechanism.
Yeah, so if you knew every player and every player got together on the internet to coordinate, then you could really get some wrong labels places. Yeah.
Could I jump in on that?
Yes, please.
Yeah. So I guess there's two kinds of coordination I would want to separate. One is beforehand, we kind of agree on what our strategies are before we see our signal. Then the task is assigned to us, we see the image, but at that point, we're kind of independently playing. That's just how equilibria work. You know, there's common knowledge of the strategies, versus a coordination that is, I see my signal, I update to my posterior, so do you, and then we get on the phone, or what, you know, we get on our apps and text, and then figure out what to report to the mechanism. That's going to be pretty much disallowed by everything that we see. By the way, one of my favorite proofs for why equilibria will always exist that are bad, we don't have any access to ground truth. Imagine there were no signals, people didn't get information. The game still has a utility matrix. It's still a well-defined game. The game has a Nash equilibrium. If both players could always take their information, throw it away, and play that Nash equilibrium, it's going to be what we would call a very uninformative equilibrium. It doesn't depend on the signal at all. There's no information being revealed by what they're playing or reporting. And indeed, later we're going to see mechanisms that try to not just make truth-telling an equilibrium, but make it a better equilibrium for players than doing something uninformative. Did you want me to swap in for BTS, or?
I think we're okay, so let's just keep going.
Great.
Yes, please.
There is no mechanism. Even if there is just no reward. Revealing the truth is always the equilibrium.
Yeah, so we'd like some kind of strictness when we think about equilibrium. We'd like, so for example, in the previous mechanism, the equilibrium was actually, if other people are doing it, then it's a strict best response to follow the equilibrium.
When there are two posteriors which are the same, like two reports give the same posterior, are we gonna be able to say?
Those would not then lead to strict preference. Cool. Let's jump into the next segment, which is going to be on a concept called the Bayesian truth theorem, which is an exceptional, also an exceptional piece of work. So what if we ask people for more information? What if we ask them actually both questions? So again, we're trying to remove the assumption that we know the joint distribution beforehand as the mechanism designer. Okay, so we could, ask, how do you perceive the dress? What's your signal? And also, how do you think others will answer this question? Okay, what is your belief on your friend? Okay, so here, again, x equals 1 means the white and gold, x equals 0 means blue and black is what you perceive. And then pi is 0.8 is when we ask this question to the class, you think 80% of the class is going to say white and gold. Okay, and 20% will say blue and black. Yes, please.
Maybe I didn't understand this, but let's assume there's no communication.
Yeah.
So my best guess of what my friend thinks is going to be what I think. So we might get stuck in a loop where...
We'll see. So there's a QR code here. And if you have the ability to get on the internet, I encourage you to use this QR code. I'm going to do it too. And we're going to collect some data.
Why is it called a QR code?
You know the answer?
No.
Oh, okay.
I thought you were Bayesian truth theoreming us.
Oh, the QR actually stands for quick response.
Quick response.
Yeah.
Ah, cool. Interesting.
So very
My internet isn't working.
You can probably get on mine. My hotspot is
Oh, then you have to join your
the password is hotspots.
hotspots.
And the password is ICANN has. Question mark. Okay, did everybody get a chance to? You see, you're not supposed to actually talk to your friends about what they think when you do this. You're supposed to actually enter what you think about your friends without talking to them. Okay, so here's the idea. Maybe if we asked for this more information, we can incentivize the agents to report both of these, all of these things truthfully. Okay, and so as we saw with a scoring rule, we can incentivize you to predict your friend, right? How can we also incentivize this report of your signal? Okay, and just a comment, there was a suggestion before, like, you know, one idea is sort of output agreement. You sort of want to reward the person for agreeing with their friend. And that has problems if the prior is very skewed, and most of the time you think that that your friend is going to say one thing regardless of what you think. And so output agreement tends not to work for these kinds of things. Here, the more popular answer would be rewarded more, so you want to just say what you think is the most popular. So we're going to need more assumptions to get somewhere. Cool. If everybody had a chance to do this, then there's a new QR code, and we can look at the results. And so if you, there's a tab at the bottom, and the tab at the bottom lets you look at the results, which is the raw data, and also you can tab to analysis. And then you can see some statistics. So you can see that the total average prediction was 0.43. Oh, wait. So the exact percentage of white and gold was 0.36. Oh, yeah, you can write it. Sure. Okay, so basically what this has done is we average the predictions for white and gold. So just looking at the P's, let's average the probability that you say white and gold. Okay, and then 1 minus that is your prediction for black and blue and black. Right, so the first two should add up to 1. Oh, is that? Oh, sorry, you're right. So this is the prediction posterior seeing. Prediction of people who reported that they saw white and gold.
I see. People who predicted white and gold, and then people who predicted who said blue and black, what's their prediction of white and gold? So you would want that to be 0.8 and 0.2 in your examples.
Yeah. Yes.
But like saw white and
Oh, like what these raw numbers?
That's the last.
So the exact percentage is the last one. So the exact percentage of white and gold. This is the true average of the X's.
And the total average prediction is how, like over like the union of like yeah I see.
And so the basically the thing that you'll see in this data and the assumption that we're going to use to try to get a mechanism to work. So we're going to have to make an assumption to get our mechanism to work, and the assumption we're going to use is that people overestimate the probability towards their own belief. Okay, so if you saw white and gold, you think that other people see white and gold with probability 60%. And if you saw blue and black, you think other people see blue and black with probability 1 minus 32%, right? So you're overestimating the number because the true fraction that saw white and gold was 36%.
Let's say I see white and gold.
Yep.
So I'm in the fraction of 0.36. My prediction of seeing white and gold. Of others would be in the average prediction of 0.63.
Yep.
But the same doesn't sound for blue and black because they're not overestimating, they're underestimating. No, they're estimating something.
This is still their estimate of how many people will say white and gold. So
Everyone is predicting white and gold. So they're predicting the opposite. They're not predicting the,
Okay.
it's not the probability the other person sees the same as you. It's the probability you see white and gold
Okay.
is the prediction.
I feel like you primed us a lot.
But yeah, so just to emphasize, so what we're seeing here kind of is what we'd expect, which is if you saw white and gold, you think a majority of people will see white and gold. If you saw blue and black, you think a majority of people will see blue and black. You only think 30%. Another thing we see is the average prediction's pretty good, I think.
Would the results be any different if instead of having us to answer 0, 1 in terms of white and gold and black and we'd answer what's the probability that we think it's white and gold, what's the probability that we think it's
I don't know if people see probabilities.
no, not probably. I can see both answers.
You can see both answers?
Yeah, I can see both colors. Yeah.
Wow.
I absolutely.
Analysis of trades that you like definitely have. Like how much money do you make? Like things that you would know about yourself, but not necessarily.
Who are you going to vote for in the election?
Like it's not just a probabilist. Like it's not a lot of the times the questions aren't really probabilistic.
Anyway, I'd love to get into the math of what we're doing here.
Yeah.
And it'd be great if in the coffee break, which is going to happen in the near 40 minutes, we can talk much more about the color of the dress. Okay, so the high level idea is people sort of overestimate the population being similar to them. So we're gonna. Sorry about that. People overestimate the probability that people are similar to them, and so they put their higher than the true thing in making their own predictions. Okay, and so we're going to make two assumptions to try to design a mechanism now. We're going to assume we have a lot of people, and in fact, we'll assume we have an infinite number of people. That's more than this room holds, unfortunately. And we'll also assume some conditional independence. Which is conditioning on something, the answers are independent. Which is, if you were to cast this into the sort of a Bayesian context, you have to say, look, there's a state of the world generating the things that in people's heads, and given the state of the world is one way, some people see this and some people see that. And so we want conditional independence conditioned on whatever is generating the whole model. Okay, so in other words, we saw one joint belief table of basically giving us this 80-20 before, but imagine there were a number of different joint tables. Okay, maybe different dresses with different color combinations invoke different joint tables. And we draw one of those at random, and then we play the game with that. Okay, so now we're randomizing over which is the dress we're showing you, and then we're asking a question about the color of the dress. Okay, and so conditioned on picking a particular dress to show you, then the distribution is independent. That's what this W is. Okay, cool. So I don't know how much of this you want me to show.
I can say I can do it on the board. Should we maybe do that first?
Let's do it on the board and see what happens.
Okay, cool. So I'll start by recapping what he said, but just put it on the board for us so that we can see it, and also what was on the next slide. Oh, can you turn yours off? Awesome. Okay, so Bayesian truth theorem. It's easier to write the formulas for n agents, so let me write it as if we have a finite population of n agents. To prove the results, as Jason said, we'll need to kind of pass to this hypothetical of an infinite population. But let's say n agents for now. And just recalling the notation, each agent I observes a signal xi. And let's say they're in 0, 1. Most of these examples, like the peer prediction example we saw before, extend to signals having many possible realizations, usually. But okay, and then this conditional independence assumption. Also, let me know if the handwriting is too small. Just let me know. So far, so good. Okay. One way to write that is that the joint probability of x1 up to xn in this case, conditioned on some underlying state w, is equal to probability of x1 conditioned on w times probability of x2 conditioned on the w, and so on, where w is some underlying, we can think of it as a state that is drawn from a known common prior, and also these conditional probabilities are known and common knowledge among all of the agents. So this is the conditional independence assumption, right? And it says that if w were known, that would kind of determine the distribution of my signal, and it would not depend on what you actually saw. Like my signal only depends on this true state w, and your signal only depends on this true state w, and so on. Okay. Good. Okay. So notation for the report. So we'll say that. Okay, it was mentioned before, and I think we're going to see it again. Agents are reporting two things: what they saw and what they think others will see. Let's just keep using x1 for their report. If we need to take a case where they're possibly reporting untruthfully, then we can use some other notation like x1 prime for a report that's not truthful. But for now, let's just say, okay, we're reporting x1. And xi for agent I, and pi is going to be their prediction of what a sort of generic other agent sees. So generally and definitely today, let's assume as well that all of these conditional distributions are identical. Okay? So for every agent, this distribution conditioned on W is the same. And so if you ask me, what does your neighbor think? It doesn't matter who my neighbor is that you're asking about. My belief about the distribution of their signal given mine, you know, there's some pi probability that they saw 1, okay, in my head. And of course, that's just my Bayesian update based on xi, right? Okay. Similar to the peer prediction, I saw my signal, and then there's this Bayesian posterior belief or prediction of what the other person saw. But now instead of trying to compute it on their behalf, which is what we did in peer prediction, we just ask them to report it. And now we, the mechanism, no longer need to know the prior because we don't have to do this Bayesian update or computation. We just ask the agents to report that prediction. Good, okay, so now I'm going to define some of the stuff that was on the next slide, but we'll just do it all at once. So the mechanism is going to use sort of the average reports and the average predictions. But actually, the two averages are going to be different functions, different types of average. So we'll let okay, this is slightly wonky, but let me keep it. X1 bar is going to be the average signal report. Okay, right. So these are all binary. This is the fraction of people who said 1. Okay, and of course this will make sense if we take an infinite population. All of this, the fraction of people who said 1, and then the slightly wonky part. But let's say x2 bar is 1 minus x1 bar, or another way to write it is the fraction of people who saw 0. Good, and as mentioned, that's equal to 1 minus x1 bar. Okay, and then the prediction averages are going to be not an arithmetic mean, but the geometric mean. If I keep writing down here, will this? Let me just go ahead and move up to here. Well, okay, we'll need the space. Move it down. So y1 bar is going to be the geometric mean of the PIs. What's the geometric mean? Remember that? Take the product, and then take the root of however many you have. Okay, so the product over I of PI raised to the 1 over n. How do you do that with an infinite population? Well, you can. The way it's defined in the formula, which I think we'll see next, is if you take a log of both sides, then it's easier to take a limit, pass to a limit as n goes to infinity. Oh, I'm sorry. Instead of y, we're using p. Let's use that p bar instead of y bar. Thanks. And then p bar 2 is going to be the same, but for... oh, good. You fixed it. OK. Yeah, let's use 0, which makes much more sense. Thank you. OK. So it's the product of 1 minus pi, and then the nth root. Or you could define it in that way as well. OK, so shall I go ahead and define the mechanism formally? Yeah, OK. So, and I'll copy this onto the board as well so that, again, we can kind of keep going. We'll still have it on the board to see. You're going to have scored on both things, right? You're reporting two things. We want to incentivize truthful reporting of both of them. And in this case, we're going to score each one separately and add your scores. Okay, and you'll get paid, or your score, your reward, is just the sum of the two scores. So hopefully we can make them sort of truthful separately in a sense. And indeed, there'll be this nice separation where your prediction score is going to depend on your prediction and other people's reports of what they saw. You're predicting what other people saw. That makes sense. And then your information score is going to be kind of the reverse. It'll be the report of what you saw and compare it to other people's predictions. And that's kind of the most interesting aspect. So the information score, what is this doing? So write it as written. So x1 bar log x1 bar over your prediction. Oh, sorry. Yep, your prediction over x1 bar. So this is the information score for agent I. That's where agent I comes in. Their prediction PI is getting plugged in right there. And then plus, well, we can do x2 bar, or x0 bar. So what's this doing? So yeah, so you may recognize this as looking like a KL divergence between two distributions, if you've seen that. Well, we'll talk a bit more later about how KL divergence can actually be used as a proper scoring rule kind of by itself. So KL divergence is a concept from information theory. I don't think we're going to directly use it until tomorrow, so I won't define it in general. But it's a measure of distance between two distributions. It's asymmetric, and this is what it looks like if the distributions are sort of x bar and pi. But the way I want to think about this is to use rules of logarithms to convert this to something that you've actually, did we actually see log scoring rule? No, okay, we haven't actually seen yet, and now is a good time to see it because it's very important. So actually, okay, let me start from the log scoring rule and get you back to this. The log scoring rule is the following scoring rule. Okay, so if R is a probability distribution and that you reported, Y is an outcome that has been observed, your score, your payoff, is the log of the probability that you assign to the outcome that actually happened. Okay, so very simple scoring rule. Actually, you can characterize the scoring rule as the only one that, basically it's the only one that depends only on the probability you assign to Y. Right? So your score here does not depend on what probabilities you assign to everything else. This is actually not true of something like the quadratic score or in fact any other scoring rule. So this is a really nice proper scoring rule. Now imagine that I scored you against one.
This is a binary case, right? So the binary case that doesn't matter.
Yeah, in the binary case, they're all sort of only a function of P probability of P1. Yeah.
So I was going to ask, like, I feel like I could have used any scoring rule here.
I think it's true. I don't think they had to use log scoring rule for this prediction score. I think you could have used quadratic. But how do we get this formula from the log scoring rule? Well, imagine I use this against one member of the population. Right, then, well, okay. There's a few steps, but if that person reported x equals 1, then I get log of pi. And so for every person who reports 1, I'm going to get log of pi. How many people reported 1? Well, on average, let's say this number of people reported 1. And I'm going to score that with log of pi. On average, how many people reported 0? This, and for that, I should get scored with log of 1 minus pi. Okay, so this is basically the sum of a proper score for me, or an average, across the entire population. Okay, now there's a slight wrinkle that you may notice, and I want to head off right now, which is actually my report is in x1 bar and x0 bar. And that could cause an opportunity for sort of non-properness. In this case, you can just fix it by subtracting me out of this, so score me on the entire population except for me. The way that we'll fix it here, which is simpler, is we'll assume this infinite population. And so my impact on this is 0. Okay, and so I can't manipulate my prediction score by reporting a signal I didn't see with an infinite population. We need the infinite population more in the other case than in this case. We don't really need it here, but it's convenient. Now, this is still not quite the information score because here we have this ratio, which makes it a KL divergence. But if you remember your rules of logs, I can convert log of p over x to log of p minus log of x. And you're actually going to get, okay, I'll do that twice, and I'll get minus an x1 bar log x1 bar, and as well as x0 bar log x0 bar, which happens to be the entropy of this distribution on two outcomes, this x1 bar, so the Shannon entropy. But the point is, this does not depend on pi at all. Right? This thing that I'm subtracting now does not depend on pi. So no matter what you predict, this is out of your hands. It just depends on what other people do. So your best response or your sort of optimal report is just going to depend on optimizing this expression. And since it's a proper scoring rule, which I haven't proved here, but because it is, you want to report PI that matches your true belief about the population's frequency of reporting the signal 1. Okay, so that was the information score. Next is the, I'm sorry. That whole thing was the prediction score. Excuse me. Sorry about that. This whole thing was the prediction score. You're predicting what the other population will do. And next we'll do the information score.
If that part doesn't matter for incentives, why did we bother adding it in the first place?
Yeah, I think it's just because I assume it's because they like the KL divergence and it's pretty. I mean, you might want something like your scores to be bounded in sort of the right range, or yeah, it's not really bounded. I mean, the nice thing about KL divergence is it starts from 0. So if you're perfectly accurate, and it actually, well, this will go down. So the best score you can get here should actually be 0. And if you're not perfectly accurate, you'll actually get a negative score. So you'll actually lose, your score will be negative. And sometimes we need to fix that by paying them a positive constant minus some number. But yeah, so you could argue that the KL divergence is a nicer score than the log scoring rule because it subtracts off. The log scoring rule sort of pays you for accuracy that sort of doesn't have to do with your accuracy, but it just has to do with the underlying entropy of the problem. And the KL divergence score subtracts off this underlying entropy, and sort of it doesn't reward you for that. It only rewards you for how close you were to the truth. Yeah, maybe you could say you prefer that. Excuse me. Still need to do information score. So I'll erase this part. Okay. And here, I'm not going to try to prove that it's truthful, but just talk about the intuition. So the information score for I, again, is, right. So let's just write it. Okay, this is one way to write the information score. Again, now we're scoring your report of what you saw. Okay, so I said I saw blue and black. Don't be mad. I can't understand how anyone saw white and gold, but that's okay. Against the reports and the predictions of the rest of the population. And we're going to use this sort of this idea that Jason mentioned previously, which is you tend to think that your answer is more common than other people think it is. This is the idea we'll talk about. First, let's just look at this. Your report in this setting is a binary xi. So what's really happening with this formula? Well, it's linear, but your report is binary, right? So what does this really mean? It's one or the other. So people, when they like to be fancy, they sometimes write this, right? What it really means, or one way to see it is, if you reported 1, you get this score. If you reported 0, you get this score. Okay. That's how I would generally phrase it, but you can put it in one nice equation this way. So the question is, for you, you can report 0 or 1, whichever you prefer. You saw, let's say, 0, but you basically get to choose. Do you want this score or do you want this one? So the idea is going to be that if you saw 1 and you update it to this Bayesian posterior, you're going to prefer to get this score. And if you saw 0, you're going to prefer to get this score. what are these scores? Well, log is just a monotone transformation. It's just, larger numbers get larger. So let's just think about these ratios. Actual fraction of people who reported 1. Average prediction of people reporting 1. Actual fraction of people who reported 0. The average prediction of how many people will report 0. So if the ratio is high, there's sort of more people reporting 1 than people think there will be, or there are, right? If the ratio is greater than 1, let's just say if this ratio is greater than 1. If the ratio is less than 1, there are sort of less people reporting this thing than people think there will be. And so that's the intuition that was mentioned earlier. The idea is with this information structure, you tend to think, well, okay. Under this simple information structure, the entire population is divided in 2. The people who saw 1 and the people who saw 0. The people who saw 1 all have the same posterior. The people who saw 0 all have the same posterior. You know that. And so basically you think there's some big group of people out there who agree with you and saw the correct posterior, and some other group of people who saw sort of the wrong thing or the other signal and have a different posterior. This is sort of an average of both of them. But you think this average includes sort of the people who are wrong as well as the people who are right, the people who didn't see the information you have. Whereas this is going to be the true population that you think you know better. So people, you believe that because of the other type, people will underestimate what you saw or what you think is going to happen. And then the similar logic applies here. Excuse me, I'm trying to sketch the idea behind why it's truthful, this is truthful, like a proof idea without actually writing any more detail.
But you keep referencing this, I think other people are going to underestimate. Is
Yeah.
that an assumption, or is that
well, no, it's going to follow from the conditional independence.
Okay.
Yeah. Like one thing that they prove is, well, they prove that the largest ratio is, okay, there are 2 ratios. The larger one for me is the one that matches my signal. So if I saw 1, I think this ratio is larger than this. Yeah, and they're saying that follows just from conditional independence in this setting. That's going to be the proof of that this is truthful. I think it's easier to see sort of why the intuition that was described earlier is not quite that this ratio is larger than this one, but it's more like, why is this ratio greater than 1? It's because why do I believe this ratio will be greater than 1? And it's because given that I saw a 1, I think there are more 1s than other people think there are. So that explains why I believe this ratio is greater than 1, and it might explain why I think this ratio is less than 1.
I guess I'm trying in my head to see if this assumption. So in my head, I'm thinking of the other example people often use, which is what is the capital of Pennsylvania?
That would be an interesting one to try and describe.
Yes, I agree. Especially in this example. What is the capital of Pennsylvania?
It's a true-false question. Is Philadelphia the capital of Pennsylvania?
Okay. Is Philadelphia the capital of Pennsylvania?
Who's heard of Philadelphia?
And
Some people think it's Pittsburgh.
yeah, I prefer to ask it this way because you get really funny answers. But they're like conditional on I know the answer.
Yeah. So and that.
I guess this is conditional independence is not very good in that question, right?
Yeah, I think the idea of this would be the capital is either Philadelphia or Harrisburg. Let's say those are the 2 underlying W's that could happen, and maybe conditioned on the W, 80% of the people are correct. Like that's all that this structure can capture. Whereas that kind of thing.
No, the W here is, again, I have all the states, and for every state I write a question, city X is the capital of state Y.
Yeah.
Right? And then I draw a random state, that's the W.
Okay, yeah, that works. Yeah, but so Nicole's talking about a description of that phenomenon is called, well, there's this idea of that experts know more about what people will say than non-experts. And so there are peer prediction mechanisms that are much more recent than this one that do the same thing. So they ask people to report a signal and ask people to predict what other people say. But you look at who is better at predicting what other people say than others, and you trust their reports more, right? So if I think sort of the wrong thing, I tend to predict that everyone will say the wrong thing or something. But as an expert, if I think the right thing, I can still sort of accurately predict that some people will be wrong if I'm more expert than others. And so the experts will tend to have a more accurate, hopefully, prediction about the population. And then you can trust their reports more as being more correct about the correct answer. So it's a super cool idea, but I think you need a more detailed information structure to make it work. All right, but that's all I wanted to say. That's what I wanted to say about this. We have a question there. Yeah.
We keep referencing this thing of, oh, the X's are like, we believe are higher than the P's and so on, but there's a subtle detail. For some reason, we chose P to be a geometric mean as opposed to arithmetic. Is there a significance to that?
Yeah, I'm sure there is that goes into the proof, but I did not prepare to talk about the details of why they chose it.
For the information square, why do you need the log there?
Yeah, I think it has to do with this, like what, because I just talked about the ratio, right? I didn't talk about the log at all. I think it has to do with this, but I think it's in the proof that I didn't prepare.
Sorry, can you explain what W is again?
Yes, so I didn't write this. So it's also common knowledge that W is drawn from some prior. It is an underlying state of the world. It's a hidden state that nobody ever sees necessarily. It's drawn from a prior and then conditioned on the W. So in Jason's example, W is a state of the United States, and then once that's drawn, we all draw information conditionally independently about what we believe the capital of that state is. In the what problem?
The dress.
Oh, yeah, I'm not sure how you would model that with the W. You could think of it as, yeah, like even
There
the
are
picture
many
itself,
dresses.
like the pixels.
We will ask this color question about many different dresses. And so we draw the dress at random and then ask you the dress, like what the color is.
Yeah, it's super important because I will say this in this literature, these information assumptions are very important because often the task, such as the dress, has lots of information in it, and you could say, okay, like, what I learned about color growing up, or the dresses that I've seen in the past. All of these things are sort of part of a signal, and whereas this structure is sort of very limited in what it thinks of as signals, and the only thing I see is my signal, not all this context. So often those assumptions on the information structure are pretty restrictive, because they also say what you don't see. Yeah.
Cool. So as I said, the slides have a bunch of references for how people did follow-up work in the single question setting. The Bayesian truth serum, which we just talked about, is one of the central influential papers here. The limitation of this is the infinite requirement that we have an infinite number of people. And maybe some of the assumptions it makes about the information people have. So after the break, we're sort of right on time for the break, maybe 5 minutes early. After the break, we'll have a review of information theory, and then we'll get to sort of the main event of this lecture, which is this determinate mutual information mechanism that YUQIN and our colleagues developed. Oh yeah.
You said that if we take our opinion out of the average, then everything just works.
For the first part of the score, so for the prediction score, but for the information score, that trick does not work.
I'm trying to remember my surprise. So surprisingly popular was also kind of a technical term attached to a paper in the late 20-teens. And I believe it had to, in my mind, it's associated with this expertise problem also. Here we had, you could call this a sort of surprisingly popular kind of idea, but I think it's a bit different in the later papers. And I think it's also Prelec, the same, some of the same authors as this one that did surprisingly popular. Yeah, I'm sorry, I'm not recalling like the details of why it, but that was another mechanism in this space for sure. Yeah.
Finite population, is there any quantification of non-truthfulness?
Discussing. In general, in some cases, yes, but I think there are some cases no, and BTS might be one where there's some reason that it's very hard to extend even to like an arbitrarily large n, and you would hope that you could do that and just get like an epsilon, like, you know, maybe it's not, maybe you lose at most epsilon utility by misreporting, by being not truthful. You could hope for such a result, and sometimes you have them, but I'm not positive that for BTS you could have such a result. And I'm not sure the reason why either. It's kind of strange, this infinite population. All right, shall we take a break and we'll see you back in a half hour? Let's do a quick recap of part one. So again, what's the idea in peer prediction? You're eliciting information from people, but unlike yesterday, you don't ever get a ground truth to score them against. And so you score them against each other, their peers, peer prediction. We saw what is called the peer prediction method, the original method in this group. And its main drawback was that the mechanism needed to know the prior distribution so that it could take your report and compute a prediction of what someone else reports. Then we saw Bayesian truth theorem, which fixes this by, well, it doesn't need to do that, but it asks people to report that prediction of what other people are going to say. So 2 reports, but it had other drawbacks. The infinite population is needed for truthfulness, and also the conditionally independent assumption on signals is also a drawback. So we're going to keep going forward in time and also forward in sort of progress to better and better mechanisms that can achieve the same results but with less assumptions. And this insight, which is really YUQIN's, due to YUQIN and her collaborators, is that there are ideas from information theory that can kind of lead us to the next step that we need to take. Am I going forward or back? I'm going backward. Okay, let's try this way. So we're going to take a bit of time out to talk about information theory. partially because we just feel this is a good topic for everybody to have seen, and partially because we're going to use it. So who's, I guess who's seen like Shannon entropy before? And who's seen something like mutual information before? Okay, yeah, so in all these cases, a good mix of people, so we won't go too slow, but we will go over it. Right, okay, so this was, let's come back to the motivating examples. Let's just go ahead into the information theory, and then we'll talk about how we're gonna use it. So YUQIN likes to present, I think this is a very interesting visual. Okay, I'm also having this, where she's going to think of entropy as a measure of information, as a sort of physical amount of information. Okay, and this analogy is going to be useful when we go to things like Venn diagrams with different random variables. But first of all, let's just write down entropy. The entropy of a random variable, as many people know, is going to be the sum over the possible, okay, let me write a capital X random variable and little x as a realization of the random variable, of the probability that capital X equals little x, hopefully we can distinguish those, times log 1 over that probability. On the slide, you see a slightly different formula. The main difference being probabilities in the numerator here, and there's a negative sign out front. And we all remember from rules of logarithms that negative log of this is equal to log 1 over this. So it's the same formula. Okay, and just a quick recap. The idea of entropy of a random variable is to measure the sort of amount of uncertainty. And so, for example, well, yeah, the more random it is, the lower the probabilities will be. Okay, and so log 1 over the probabilities will get larger, and this entire thing will get larger. Okay, so something that is spread out over many, many outcomes with very small probabilities has very high entropy, lots of uncertainty. Okay, there's a lot more one can say here, but many of you have seen entropy, so I try not to say more unless there are questions. And a lot of what we've seen right there, we have different random variables. So there are different signals that different agents have, and there's also often sometimes this sort of state of the world that's influencing the signals. And so the entropy of these things is going to play a role in what comes next. Let's continue talking about entropy as uncertainty. So for example, a distribution that is uniform on 2 outcomes has higher entropy. It's more random. Wow, how much did we skip? Okay. Then we didn't find out the secret. Okay. Then it has more entropy than this smaller circle, which is the entropy of a random variable with 70% on one outcome and 30% on another. Okay. This is a bit more certain. It's a bit less random according to the measure of entropy than this one. This has the same entropy as this. Entropy is the same if you permute the probability distribution. Okay, so there's a few different pieces of information theory that are worth going over. And YUQIN gives us a nice analogy to set operations. And I will try to keep track of them here. So joint entropy is h of x comma y. This is just the entropy of x and y. Okay, the comma is just joining them together. And it looks a bit like a set union operation of, let's say, x union y if these were sets. Let's see the picture. So if the entropy of x is the green circle, the amount of entropy is the size of the green circle. The amount of entropy in y is the size of the yellow circle. The amount of joint entropy that they have together could be the size of the union of the circles. it's smaller than the sum of their areas because there's an overlap. This overlap can occur due to some correlation. Trying to think of a quick example. All these examples are too complex.
Sometimes you and Jason talk at the same time.
Okay, so I'm going to say a sentence. Jason's going to say a sentence. There's entropy in each of those random variables. Okay, but certain types of minds think alike. We're not going to say which types, but the joint probability, the joint distribution of those sentences is not sort of twice as uncertain as the entropy of one of those sentences, because the things we say do tend to be correlated. And so, yeah, the more correlated the variables, the more overlap. If x equals y with probability 1, they're the same random variable, this would be the same circle superimposed. If x and y are independent, as you'd expect, the circles would have no overlap, and the joint entropy would be the sum of the two entropies. But here we see this inequality that it's always less than or equal to the sum. The formula, you can just treat it as the entropy of pairs x comma y and apply the entropy formula. We're not going to use most of these formulas too much, so I won't spend lots of time on them, but the concepts are nice. Next one is conditioning. So conditional entropy, h of, let me remember. Okay, actually, yeah, we're going to use E because we're going to have this idea that E is an event that we want to predict, and X is information that helps us predict the event. And we're going to talk about the entropy of E conditioned on X, and that's going to look like a set difference in our analogy. E set minus X. So the idea of conditional entropy is going to be how much uncertainty is there in E after I tell you X. Okay? H of E was how much uncertainty is in E. Excuse me. Blue is E. This other blue is X. You started with a lot of uncertainty about E, and then I told you X, and it cut out a lot of this uncertainty because they're correlated, and so you do a Bayesian update on E, and now you know a lot more about E, and the amount of uncertainty you have is smaller. That's H of E given X. Good, okay, so the formula is, again, the formula for entropy applied to the probability distribution on E conditioned on the outcome of X that you've seen. So that's this formula here. Excuse me, it's the expectation of that over all outcomes of X that you could see. So the sum over pairs, the probability of the pair, but then we're taking this log of the conditional probability. And because of the rules of logarithm and because of the definition of conditional probability, which we don't need to go into today, but we do need to tomorrow, so we'll do it then, you can rewrite this and sort of factor this out. It turns out to just be the joint entropy minus the entropy of X. This turns out to be an equality. It's not super obvious. Okay. Stop me if there are questions, but I probably should err on the side of going fast than slow, so yeah.
Is one question about like the formula. Why is it that this is not probability of X condition of E?
Yes, so you could write this as the following. An expectation, well, let me just write it this way. A sum over X, probability of X, times the entropy of the distribution, E conditioned on this particular outcome. That's the sum over E, probability of E given X, log 1 over probability of E given X. And you'll see that this is equal to that formula. So yeah, it's an expectation over what you see from X of how much you'll know about E after you see that. So some realizations of X could tell you a lot about what E will be, and some could tell you a little. And we average over those for this definition. Thanks.
It feels like you're overloading notation a little bit between h of x and h of e given x, maybe.
Yeah.
That's why there's the confusion.
Yeah, you could argue this notation is hiding too much, or it's too ambiguous. Sorry, I just want to keep my column clean. Excuse me. So the last one and the most important one conceptually for what we're doing today is mutual information between two random variables. Well, excuse me, we're not using H anymore. We're going to use I of, I think we're going to do X and Y here. Let me just check. Nope, we're still doing X and E. We use the semicolon, so we get some more nice overloaded notation. And the intuition that this corresponds to in our visual is set intersection. Okay, so E intersect X. And yeah, so it's kind of a measure of correlation in a sense, but it's a bit more, entropy driven than that. How much information is in both X and E? How do you do that in a formula? This way. This one doesn't kind of break down into kind of just reducing to entropy. But the key idea is this ratio of the joint probability of a particular pair, XE, over the product of the marginal probabilities. So if X and E are independent, this ratio, someone help me out? It'll always be 1, and therefore the mutual information will always be 0, because log of 1 is 0, and you'll just be summing over a bunch of zeros. So for independent variables, the mutual information is 0. I said earlier this intersection between independent variables is empty. But okay, so this is the formula, and you can also rearrange this with the rules of logarithms as the entropy in E minus this conditional entropy. And that also matches the physical analogy here, right? The size of the intersection is the size of the entire blue circle, all of the uncertainty in E, minus the size of this slice on the outside. You're left with the intersection. And all of this is kind of in units of bits of information, if you've seen information theory. So this is kind of how many bits does E contain in it? How much uncertainty is there? How much information does E have? This is how much information does E have if you're going to get X first. And the remainder is kind of this, what's in both E and X. You could also rearrange this to get the same formula with roles reversed. You could rearrange it to get H of X minus H of X given E, and it would also be equal. Yeah.
That sum is over E and X.
Yeah, the sum has got to be over both E and X. Thanks, yeah. We're going to use this, but we're not going to use the details of the formula. So yeah, I think I won't even copy it down because I don't want to emphasize how the formula works. I really want to emphasize the intuition, and that's what YUQIN's intention with this analogy, which I have found helpful. So this is the most important concept of the ones we've discussed, is this mutual information. Okay. And we'll see, how can we bring this back to this idea of people reporting different pieces of information to our mechanism, and trying to assess that information against each other. Okay, so I think that's the end of, oh no, okay. This we definitely won't need technically, but let's mention it. How you can kind of, nope, continue chaining. So you can talk about the mutual information of X and E after I'm going to learn something Y, right? Condition on Y. And all of these concepts, you can chain to larger strings of random variables. Okay, so the peer review example, I have to recall exactly how it fit, but luckily YUQIN gave us a nice summary. Good, okay. So the model of the world for this example, I believe, is the following. Remember we had this sort of, for Bayesian truth theorem, this model with a state of the world that is underlying, and then signals are generated independent conditioned on that underlying state of the world. Let's imagine here that a paper that we're reviewing, where each peer reviewers, has an underlying quality that is drawn from some prior, that is either accept quality or reject quality. And then I'm going to get a signal X that is distributed, and perhaps it's independent of what you see conditioned on the true quality. And then you're going to read the paper and you'll get a signal Y that's distributed according, conditioned on the true quality. Or maybe there's some other correlation in here. X and Y might be correlated in some ways, not just based on the quality, but on something else. So for example, we both really like peer prediction. If it's a peer prediction paper, our reviews might be correlated with each other on top of any correlation that comes from the state of the world that we're trying to estimate. So the mechanism designer wants to collect reports from us and estimate this state of the world. Okay, and we're not going to, this is just a motivating how the idea of mutual information could start being helpful, because you can measure all these quantities between all these different things. So you can look at mutual information between X and Y. How much do we kind of tend to agree? How much does my review let you predict what your review will be? Let someone predict what the other review will be? But then also, how much does my review tell someone about E, given we already have a first review, right? What's the information, mutual information? Well, okay, that might also, the way I phrase that might be more of a conditional. No, that's the right way to phrase it. How much does my review tell you about the true state, given that you already have somebody else's review? So we're going to try to use this concept in peer prediction. And that's, well, we'll see, yeah. Okay, so an aside that we've kind of run into now in the first part. So we've seen the log scoring rule. I like the log scoring rule. I'm going to write it again. It's just one of these things I find calming is to write down the log scoring rule. So S of, wait, P, are the roles here reversed? Oh, okay. P is the underlying distribution of Y, but let's just write down the log scoring rule. So S of Ry is log the probability that, okay. Let's write this again in the binary case as we did before. So R is going to be a probability between 0 and 1. If Y is 1, excuse me, you get log R. If Y is 0, you get log one minus R. Remember this idea from before? So Y is just selecting which score you get. So you predicted an R probability that it's 1. If it is 1, you get log R. If Y is 0, you're going to get this, which is the probability that you assign to 0. So that's the log scoring rule. And now if I have a true belief, for example, a true belief P, then I can look at my expected score for any given report, given that the outcome will be drawn according to P, my belief. And there's actually a notation that Jason mentioned for this yesterday that I like to use as well, S of R semicolon P or something like this, scoring your expected score for this report with this belief. In this case, what's it going to be? Right, so according to my belief, with probability P, Y will be 1. And I'll get this score. And with probability 1 minus P, this will happen, and I'll get this score. Yeah. Okay. It was nice that this ended up being linear in my in my belief. It would be nice if all scoring rules were linear. Oh, wait. Scoring rules are linear in your belief. We'll talk more about that tomorrow. It is something that Jason mentioned yesterday. So, okay. So this is the expected score. You could maximize this over P, and you would find that for any given R, maximize this over R. You'd find that for any given belief P, the R that maximizes this expression is going to be R equal to P. You should plug in P here if you can plug in any number you want to maximize it. Okay, so recap on the log scoring rule in a bit more detail. You'll see this formula more. But there's a connection to Shannon information theory, which is super nice. If I can pause on the correct slide, sorry. Yeah, okay, this is just a picture of Bayesian updating that we've seen, but let me talk about the connection to information theory. So this idea of value of information, right, that we talked about, this is still kind of part of the information theory section, I guess. I didn't signpost that well. So let's just take a second to recall value of information from yesterday. Again, this is something that we're going to talk a lot about tomorrow as well. This is your expected score. If you're predicting your posterior belief, conditioned on the fact that you saw some information X. We recall this? This is your, we might have seen this in a slightly different format, so stop me if you're not recalling it. This is just your expected score for reporting the prior before you saw any information. The gap between these, at least the expected gap between these, is the value of information. And Jason had a nice drawing for this with this convex function. Well, I think in our case, we mostly focused on a convex function, which looked basically like this. And if we reported the prior, for example, we got an expected utility in our decision problem or an expected score of our scoring rule like this. And if we waited and got information and reported the posterior, we either had a posterior of here or here. And the average sort of score or utility after getting the information was higher. The distance between those, the vertical distance, was the value of the information. Is everyone seeing that? So that's a reminder. You can do the same thing with any scoring rule, and in particular with the log scoring rule. It turns out to be super nice. I think I'll probably skip the math and just, oh, okay, I get the math on the slide, excuse me. The value of information here is the Shannon mutual information between Y and X. Sorry, I've switched to E and X now. And yeah, I guess a proof is to kind of go through the math and kind of math it out. But another way to see this actually, well, yeah. Let me say a proof out loud, a different proof out loud as well. The expected score for the log scoring rule, if you're truthful, turns out to be the Shannon entropy of your belief distribution. Well, actually, it's the negative of Shannon entropy. Shannon entropy is the following concave function well, it's this one, and it looks like this on 0, 1. The expected score for the log scoring rule as a function of belief, if you're being truthful, looks like, well, it's the negative of Shannon entropy. And this is the same convex function G that was coming up yesterday with Jason's value of information. So this, yeah, anyway. The expected score in the log scoring rule is a Shannon entropy, or the negative of a Shannon entropy. So the first term will turn out to be the conditional Shannon entropy. The second term will turn out to be the entropy of E, the original entropy of E. And when you subtract those and remember some formula for a while ago, you get the mutual information. And I like all of this because the units of the log score now are sort of in bits of information, which I think is very cool. Right? So your expected score is how many bits you're providing of information about the outcome, which is super cool. And this difference now is how many bits of information did you get from X about E. So it's a cool idea. We're not going to use this again super technically, but it's nice to see what the technical part is once. But yeah, questions there? Okay, so I think we now get to start applying it back to some peer prediction. So, right, approach for removing the posterior oracle. This was in peer prediction, the idea that if someone reports a signal to me, I compute on their behalf a posterior belief about others, and we use that in the mechanism. Can we get rid of that assumption that I need to be able to compute the posterior belief? And here's an intuition for it, for something you could try to do. Right, which is, well, okay, it's, oh, I think I wasn't, oh, you did? All right, can you chime in for me? Thank you.
Yeah, so the posterior oracle mechanism, recall we rewarded player 1 based on, some scoring rule S, which is based on we know if we have the posterior oracle, we know the posterior given your signal x1. So based on putting your posterior that we know given your report x1 for evaluating x2. Okay, so the first thing that we're going to do to adjust things is we're going to subtract a constant from this scoring rule. And the constant we're going to subtract is just the score for the prior and x2. Okay, so given that we're the mechanism designer, we know what the prior is, right? And so so x2 does not depend on the report x1. So this is a constant with respect to player 1. So player 1 doesn't care if you just subtract a constant from their score. So the incentives are the same. Okay. And then the next thing I'm going to do is, instead of using the quadratic scoring rule we used first when we introduced that, we're just going to plug in the log scoring rule instead. Which doesn't matter to us for the incentives, which scoring rule we use. And so now we see that the thing that we're scoring people on is exactly the Shannon entropy. Okay, so we're using is exactly the mutual information. So the score that player 1 gets is the mutual information. And what's interesting about this, from what Bo suggested before, is the score for player 2 is also the mutual information. And the mutual information is symmetric, like it doesn't matter which way you do it, right? It's the same intersection of the two sets, right? Is what's correlated between them. Okay, and now that you see that mutual information is a good way of doing it, if you knew all the stuff, so we had to know the prior to compute the mutual information to do this. But maybe there are other notions of mutual information besides Shannon entropy that have better properties. Do you have the clicker?
Yes.
Okay, so what are some important properties of mutual information? So if we have independent we're trying to generalize Shannon mutual information to sort of what was sort of important for making the incentives good. Okay, and one property is that if we have independent random variables, then the mutual information is 0. There's no mutual information there. And the other property that mutual information has is what's called the data processing inequality, which says that if one of the players adds noise to their report, that can only lower the correlation between their report and the other player's report. You can't sort of increase correlation by adding noise. The only way to increase correlation, in other words, is to add something that's actually using information that's related. But if you only knew what you knew, you have no extra information you can add. You can only add stuff that's independent of the other player. Okay, and adding independent stuff just sort of, potentially makes the information worse. Like, for example, if, we were asking a multi-dimensional reporting question where you could, instead of saying just, is it one color or the other color, you could say, is it one of these 5 different colors? And one thing I could do is every time I think it's red or green, I just say red. Okay, now if the difference of red and green is more correlated with the other player, I've just lost information. And now it's sort of less accurate. And so I'm lowering the mutual information. And so the idea that's going to be very powerful that we'll see shortly is that, well, applying a strategy to your information and reporting something else if you have no idea what the other person is thinking is like data processing. You have your signal, you do some processing to it, you produce a report, right? And so that should only lower the mutual information. And so if we use any notion of mutual information, anything that satisfies these 2 properties, it should be a good strategy just to report your signal truthfully, right? Because anything you do is going to just make it less mutual information, which lowers your payoff if your payoff is mutual information. Okay, so Shannon defines this mutual information. There are other definitions of mutual information maybe we could think about using. And what we'd really like is a mutual information that we could define without having knowledge of the prior. So the Shannon one doesn't work because we need to know the prior to do the Shannon one. And so the rest of our discussion today is going to be on looking at notions of mutual information that we can actually implement in a real study. So with a finite number of participants and a finite number of questions we ask them. And so that's going to be sort of the goal coming up. Cool. What's our strategy for this part?
You saved me when
I can turn it off.
Oh, yeah, that's right. Yes. Cool. Okay, so we're going to see examples of the idea that Jason just mentioned, which is, again, this using a mutual information-like object, not necessarily Shannon mutual information, for peer prediction. And a lot of these, YUQIN has pioneered. And we'll tailor that to the time so that in 50 minutes we stop. Okay, so we're going to this multi-question setting, so let me explain what that means. The number of questions we asked to the agent, or the number of things we're interested in so far, has been 1. I want to know one thing. For example, what's your opinion on the color of the dress? In any other examples, we go to the agents and we ask about one thing. We might ask multiple pieces of information about that one thing. In Bayesian truth theorem, for example, we asked, what do you think about the dress? And what do you think about others about the dress? But it's one question in the sense that it's one task, let's say. We'd like to remove all the assumptions and still have a mechanism that is truthful and incentivizes people to report, good information with one task, but it's challenging. And an idea that came up in the literature is, well, in a lot of these settings, you're actually doing lots of tasks anyway, right? So for example, this is applied in things like crowd work and image labeling. I have a lot of images that I need labeled, I take each image, I show it to one person, I get a report, I show it to another person, I get a report, and I use that. That's one task. And then the next image comes. If I'm asking them lots of questions anyway, can I start looking at their responses across the different tasks and how those are related to each other to try to get truthful reports on the set of tasks? Okay, so that's called the multi-question setting. And it won't surprise you that that's going to play really nicely with this idea of information, Shannon information or mutual information. Okay. So generally, we're going to always make this kind of assumption in this setting. Papers, I believe, weaken this assumption a little bit to different respects, but not a ton. We often have this. It's a sort of a priori similar assumption, which is that these tasks, before agents get any signals, the prior distribution on the tasks is sort of the same, symmetric. Okay, each task is symmetric with another in the prior. It's not exactly, like there are different technical, I believe, ways to write down that assumption. A similar assumption that goes with it is going to be consistent strategies, which is that the agents treat the tasks the same. And this is going to help us a lot if we can assume that, and we generally will assume it. What do I mean by treat the tasks the same? Well, if you think of a strategy such as truthfulness, I'm truthful on every task. And now if you think of a deviation, we're going to assume that if I want to deviate to some non-truthful thing, like, sometimes when I see a dog, say a cat, I need to apply that deviation in the same way to all my tasks. Okay, I'm not going to be able to deviate in a way where I take some subset and wisely flip those to dog, but I take this other subset and flip them to cat. I'm not able to do that. Excuse me. The consistent strategies assumption makes sense with this a priori similar tasks assumption, right? The tasks might even arrive to me sort of randomized, and the tasks are maybe presented to Jason in a different random order. So trying to coordinate on flip your answer on the third task, and the fifth task won't even work because his third task might not be my third task. So any deviation strategy we want to apply would kind of need to be consistent and the same for all the tasks. So we'll often make that kind of assumption will be important for this.
Did you relax this assumption?
I believe the literature does not relax that assumption much. It's not quite, okay. I think I'm going to write down some specific models later. Okay, and then we can ask the experts as well. It's not quite like IID, but it's kind of pretty close. And I think the results need it so far. Okay, so here's a bunch of the literature on this. So this paper was the first, Dasgupta and Ghosh 2013, to use this idea of multiple questions in this setting. And it kind of had this cool mechanism that worked, but people didn't know what else to do for a while. And eventually this paper, which we'll probably discuss briefly as well, generalized it significantly and sort of explained why it worked through the framework of mutual information. Okay, and so we'll talk about that. And then some things came after that, and we'll jump ahead to this determinant mutual information mechanism, which is really cool. And that'll, this will still share some drawbacks of prior work, but it'll show the way, use mutual information. This is going to give a mutual information measure that does everything we want, this DMI mechanism in this setting. Okay, so excuse me, let's explain this model more specifically. So the general idea is that we're doing sort of binary labeling. So the signals are going to either be -1 or +1. And the agents are going to be assigned a set of tasks now. So a task here is a row. And each agent is assigned multiple tasks. And the agents are assigned the same task. And we're going to compare not just what you said on this task to what Bob said on this task, but we're also going to be using information about what you said on other tasks and what Bob said on other tasks, even to score you on this task. Okay, how should we use that information? Actually, let me leave the idea up here and start putting a more detailed model on a board, and just to make sure that we have a detailed model for this. Let me leave that here so I don't. Okay. So let's say there are m tasks total. And n agents. We don't need infinitely many agents. Actually, we could just have 2 agents. That would be fine. We do need more than one task. Actually, I think I forgot to write down how many tasks we need. It probably works. The theorems probably hold on 2 or more tasks. But often you can kind of do better if there are more tasks. And let me just write down the information structure so that you have another example of an information structure in these kinds of settings. So each task is going to have an underlying state, and this is going to look kind of reminiscent of the Bayesian truth theorem. So it's either high or low. So for example, sometimes people apply these kinds of models to things like ratings or recommendations or reviews. So let's say a task is a restaurant that we all went to, and you want to rate it, and its underlying ground truth quality is either high or low, okay? From some, according to some prior. Okay, and then I's, okay, in this notation, I receives a signal on task let's use, I really want to use J. Yep, okay. On task J of, in this case, I'm going to call it xij with a hat, just because I'm trying to follow the paper's notation. In -1, 1, which is their true, which is the signal that they receive that's distributed according to some probability of 1 given high, excuse me, and so on. So probability of 0 given high is equal to 1 minus the probability of 1 given high, of course. And then similarly, given that the true state of the world is low, there's a probability that I'll see a signal 1 and a probability I'll see a signal 0.
Is it bigger than 1/2?
I don't think they need it to be bigger than 1/2, actually.
That's it. You
Am
can
I-
always use it. If it's smaller, then you use the other signal as signal if you want.
Yeah, I mean, it is kind of motivated to elicit someone saying, I saw a high signal even though I know it's in the minority, or even though I believe others won't see it. You know, that's kind of the hard case, is to elicit such information. Is there, so far so good? Okay. Okay, and then again, in this paper's notation, the report, I will make a report, xij, which may or may not be truthful on task j. And now the idea is that every task is, in a probabilistic sense, independent. And they all have this information structure. Sorry, I didn't quite say. Let's go ahead and say that the agent I's signals are conditionally independent. I don't think, I didn't actually write that down. let's say for now that the I's signals are independent conditioned on the true state, just like they were with Bayesian truth theorem. However, I'm pretty confident that this extends beyond where I's and J's, yeah, it must extend beyond where I's and J's signals can have correlation in them. So just kind of a joint distribution of I's signal, J's signal, and the underlying state should be allowed. Do you agree off the top of your heads? In this, okay, the paper is a bit older by now, but I believe that's the case. Because that's part of the point, is to weaken the information structures. But it is key that the tasks are probabilistically independent. So one task has a lot of correlation in it now, or it can have more correlation and information in it now, but the tasks are independent from each other according to the prior. Okay, and each agent does T tasks. So okay, cool. So what's the idea of what we're going to do? It's not going to look that much like mutual information until we start squinting at it later. But, well, okay, we keep talking about information and correlation as being very related concepts, right? Two variables that are very correlated, you might think have a lot of mutual information. That's a rough intuition. Variables that are independent are also not correlated and don't have mutual information. This is going to literally use a measure of correlation, like a formalization of what it means to be correlated. And to see the idea, let's look at these two different report profiles that could happen. In this profile, what happened? Alice said 1 on every single task. Bob said 1 on every single task. Well, is this good or bad? It's good in a way, because this could be what happens. You know, they're agreeing a lot. You know, maybe that's just the way the world is. But it's bad because this could easily be some sort of low effort type. That's an informal term, but coordination. We agreed beforehand to just always say 1. So this could be a problem.
But even if you have 1 minus 1, 1 minus 1, 1 minus 1, but you have a perfect diversity, you could say here or something, because you have half each, then you could also have coordination. Also, if you're only doing T tasks over the M that you have, then these could be the ones, right?
Yes. So our assumption of this, the a priori similar tasks, which I've formalized here by independence across tasks, but I think we also need the consistent strategies, random order type stuff, means that coordination of the form report 1 minus 1 alternating all the way down is not possible. So one way to try to help enforce that is to give you the tasks in a different order than I give them to someone else, so that it's hard to do such coordinations. Yeah, but that's what you have to worry about, exactly, is more sophisticated forms of coordination than just all ones or something. So if we've managed to, you know, such an assumption can be justified by a peer prediction type setting in which, for example, crowd workers are at computers in different parts of the world, perhaps, and it's not necessarily easy for them to communicate, and we can enforce some of these. So this is viewed as probably a good outcome because, first of all, they're agreeing, which might mean high accuracy or something. But second of all, they're not doing the same thing every task either. How do we formalize that? And it's going to be this idea of the expected value of Alice's answer and Bob's answer minus the marginal average of Alice's answers and the margin times the marginal average of Bob's answers. And basically, this is it's almost going to be our score. Yeah.
Sorry, I'm just back to the diversity thing. But isn't that like making you change what you would answer? Because you have to be diverse in order to get the payoff?
Yeah, so we're going to see that
Making it more like the more certain you are, then you're going to put that so you can left for the things that you're not that certain the other one. So how?
Yeah, it's interesting. We're going to do this in a way that is still truthful, which is maybe surprising. So if it is going to be truthful, then I might wish that the tasks themselves had more diversity in them, because then when I was truthful on those, I would have lots of diversity and get a good score. But I'm not going to misreport and pretend there's diversity when the true answers are 1, 1, 1. If the true answers are 1, 1, 1, I'll still want to do that. I'll just be sad. I'll get paid less. Yeah. You won't get paid very much. Yeah. Yeah. So then you can join a union.
I think the point is that adding diversity, for example, by randomizing, the diversity also has to be agreed upon by the other player, and there's no way they can agree with you. And so that's actually not going to help you to just fake diversity. So you need diversity. You need to agree on the diversity for it to benefit you. And since you can't communicate with the other player because they see them in different order, there's no way to introduce diversity that they agree on. Yeah, and so this first term, again, this is like the expected value when they're correlated minus the expected value when they're independent, right? As if they were independent. And so this second term is basically assuming you just re-randomize everything to make them independent. What would it look like? And as you can see, that if you were to try to add diversity just by adding independent noise, that's going to look like the second term anyway. That's just going to get subtracted out at the end anyway. So it's not going to benefit you at all to add that kind of diversity.
Yeah, another comment.
Two examples of extreme cases in which the first case they will get 0 and the second case.
Yeah, I'm going to write down the formula, but in the first case they'll end up getting 0. In the second case they'll get a good score.
The maximum.
It actually is the maximum for 3
Because
tasks.
if they agree to start, both of them, they agree to start with 1, and then the second one is -1, and so on.
Right. So this goes back to the idea that we need to avoid them being able to coordinate on, like, yeah, agreeing to answer, for example, the second task with -1 only. And
They just say 1 and -1. If they are coordinated on this, that's fine.
so, for example, let's consider let's consider 2 tasks. And I've sort of asserted so far that it's better for the agents if one answers 1 and the other is -1, and they agree. Well, depending on the information structure, but pretty much always in the information structure. They could try to say, hey, let's get some diversity in our answers by each of us answering a 1 and a -1. But the problem is, if the tasks are these a priori similar tasks, actually, you might need the consistent strategy. You could agree to randomize 50-50. But if the tasks are a priori similar, our randomization is most likely going to result in a mismatch. So I say 1 when you say -1, and I say -1 when you say 1, or at least there's a reasonable chance of that mismatch, and that will hurt you more than just saying 1, 1, 1, 1, or so on would benefit you. Well, being truthful will always be the best, and we'll talk a little bit of, well, actually, I'm not sure we'll give a lot more than this, but we'll talk about the mutual information idea. I'll write down the reward function. I mean, it's pretty much that. So your reward is going to be some quantity aij this is the reward for I on task j. So for every task you do, you'll get a different reward. It's going to be some quantity aij minus a quantity bij that I'll define, where, well, we're going to pick a reference agent to compare you to, and I'm going to call them I prime. So I prime is some other agent, and we call them the reference. Okay, and then AI is going to be the first term in that, and then BI will be the second term. AIJ and BIJ. AIJ will be, oh, you know what? I wrote these down for the 0, 1 setting rather than the -1, 1 setting, and I need to adjust. Yeah, it's a lot simpler in the -1, 1 setting because I think it's just this. Okay. Let me make sure this is clear. Okay, so the first term is just what I said on task J and what I prime said on task J multiplied together. If they say the same thing, this is +1. For example, if they both said 1, this is +1. If they both said -1, this is +1. If they said different things, this is -1. If they disagree, this is -1, which is going to be bad for them. Yeah, okay, so, okay. What's the disagreement aspect going to be? Right, it's going to be xi on some other task k, and xi prime, the reference rater, on some task L. All three of these need to be different. So actually, we do need at least three different tasks in order to define this mechanism. So what's going on? This is what agent I said on some task that's not the one we're trying to score. And this is what the reference agent I prime said on some other task that's also not the one we're trying to score. If you remember back to this idea that Jason told us about, where we take the original peer prediction mechanism, which was a sort of score of how good you were doing, and we could subtract off this sort of score of the prior. This is kind of like an estimate of a sort of score of the prior, in a sense. Like if you didn't know anything except you knew that sort of a random report was this and another random report was this, this might be a kind of score that just sort of guessing according to the prior could get you. And when we subtract it off, we get something that's sort of a notion of a mutual information between agent I's vector x and agent I prime's vector x. You could also average this over lots of tasks, and it would look even much more like a mutual information when you add this up over all the tasks and average it. Okay. Oh man, we're not out of time yet, right? Did it just go into screensaver? Okay, so I didn't plan to prove this, and probably for time it's good because we should talk about the determinant mutual information mechanism, and we have one thing to do before we get there. So let me write the theorem. I've said it out loud, but and you know, I haven't written every single assumption like this a priori similar task consistent strategy. I haven't written everything down. You know what? Someone said this, and the theorem that I am reading does have an assumption that you need the priors greater than 1/2. Yeah, which makes a lot of sense because this is based on agreement. So you are going to have this assumption that the probability basically yeah, we're going to fix that later. YUQIN will fix that later, but for now, this assumption that probability of agreement is sort of greater than 1/2 in beliefs. So if so, under all the above assumptions, then truthful reporting by all agents on all tasks is an equilibrium, a Nash equilibrium, well, or Bayes Nash. I believe there's a strictness condition here that I haven't copied over. So again, the idea that not only is it an equilibrium, but if you deviate to some non-truthful strategy, you do strictly worse. And there's some addendum, so I won't write it down, but if the tasks are, for example, this a priori equivalent, then this equilibrium actually yields maximum rewards to all agents over all strategy profiles, anything that they could try to do in this mechanism. The truthful equilibrium is the one that has the sort of social welfare maximized. And why? Again, it's sort of the mutual information idea. They're revealing the most information by being truthful. And anytime they try to switch to some strategy that's deviating and not being truthful, they're introducing noise into these vectors. And noise is going to decrease how correlated you are with someone else, because the only thing you have in common is sort of this truth. And so mutual information sort of says that the more information you provide, the higher your score. And that's basically the proof as well. But yeah, we're not going to get into it. Yes?
Quick thing about all this model from the beginning. You reward people about something important, and then as if it was the end of the world, but then there will be a decision made. Right? The decision maker
okay.
based on the report. But maybe the
Yes.
decision is not more important than the reward I'm going to give them, and so they don't care at all about my so this is related to the value of information.
Yes.
So is there any development once there is something happening after that? Or
Yeah, I would say generally very little is studied in this literature with an idea that I have an upstream task and this is a step in that task, but I want to maximize sort of my utility, which includes like paying them just the right amount to get good information, but not too much, and then making a decision based on the information and only collecting the information I need for my decision. That would be really cool. I don't see much like that. Maybe a little bit where the task is machine learning and this is data and we have a goal.
Example. Imagine you give money to people to give their prediction and what they're going to vote for election.
Yeah.
The election is very important for them. So
Yeah.
this information may coordinate everybody to vote for the candidate I dislike. So I'm not going to give this information if you give me a little bit of money, for example.
Yeah.
Many examples like this.
Yeah. So I don't know of much like that. It's possible some a little bit is out there like that. And it'd be really cool. I was talking with some people over break to bring in the idea of optimization of scoring rules here as well, which is if I'm going to buy information, I might as well choose a scoring rule that pays most efficiently for information. Yeah. Question?
And secondly, here you assume anything about the infinity of population. There's no infinite number of.
Oh, right. Yeah, population, I believe.
Nothing, so what is assumed here?
Right. I believe the population can be as small as 2 agents, and this, for any.
Probability here. This is the quality of signals. Informativeness of the signal that we receive should be positive.
Oh, like something about this. Yeah, I think. I mean, if like for example, if these were all equal to 1/2 or something, then you would always expect to get 0.
What do you use as assumptions? Because at the beginning you said, okay, we know that we should know the prior, blah 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 blah.
Yeah.
Make it work. So now
Yes.
what are the assumptions?
Here's definitely a setting under which the theorem holds, which is what I've tried to write out completely on the board. So every task is statistically independent. Every task has a prior on a ground state of the world, which is either high-low, common knowledge among all agents. So once you get the task, you know what this
There is no assumption on the
prior
number
is.
of tasks. It can be one. It can be.
Tasks need to be at least 3 for this to be well defined, and I'm pretty confident that 3 suffice if you have 3 tasks
3 tasks or more.
and 2 agents or more. Yeah, if you have more, then you can kind of select these references. Yeah, 2 agents, 3 tasks would be good. Yeah, great, thanks. Okay, I'm not sure how we got to this slide. Let me go back. How many times? Yeah, this is about where we want to be. Okay, so I will not say too much about this this work, but I will say a bit. This work I would describe as bringing us the idea of mutual information, right? Like this mechanism was defined, but no one thought of it as a mutual information. They're just like, this is an interesting thing to do that works. So this brought us the idea of mutual information and said we can generalize this. But there's a problem, which is actually something Jason mentioned earlier. A lot of mutual informations you want to use aren't necessarily going to be implementable in a way that you can actually estimate them from a small number of tasks, for example, or at least not in a way that's incentive compatible. You might try to estimate the mutual information, but you're doing some complicated formula with like Shannon entropy in it, and agents can misreport a bit and game your formula. So it's a problem. Yeah, sorry. Here. So this paper recasts this as this mechanism and then also another mechanism as special cases of F mutual information, which is a generalization based somewhat of Shannon mutual information. So for kind of background and flavor, I'll define that for you, but we won't get too deep into what F mutual information is. But let's go ahead and just define it, because it's kind of a useful notion to know, and I think the recitation will have some F mutual information stuff. Yeah, okay. So we won't be going in with too unprepared. Okay, so given a convex F, all right, we might be moving to the wrong slides, but we'll. Okay, I don't think we've defined a convex function yet this week. A convex function is one that looks like a smile. It's one where if I take the value of the function at 2 points, the average of that is always higher than the value of the function at the average of the 2 points. Okay, convex function. Given a convex F, you know what, that definition might not quite work in all dimensions, or at least not in like infinite dimensions, but it's good enough. The F divergence between two distributions P and Q is defined to be the sum over Y. Here I've done it with Y. Q of Y, the probability that Q places on Y, times F of P over Q. Okay, maybe you define a slightly different version in the notes, or in the recitation, but hopefully it matches. You can switch the order of arguments, for example, and not really change anything, but we'll go with this for the lecture. Good. So given any convex function, you can define this as sort of a distance measure on two distributions, how far apart they are. This is different than the Bregman divergence, which has probably been mentioned this week and will be mentioned more tomorrow. Those are kind of two different ways to take convex functions and make a distance out of them. This one is specific for probability distributions, for one thing. That's a bit different. Quick examples. If we take F of P to be, no, I'm sorry. F is a function, F is just a function on, the reals are on 0, 1 to 0, 1. Right, F just takes a real number and outputs a real number. Actually, yeah, not 0. So F is just some function from the reals to the reals that's convex. So an example could be F of, let's just say Z is Z log 1 over Z, or Z log Z. Z log Z. Turns out this is convex. Don't ask me to prove it in real time. It's a convex function. You know, my graphing calculator says so. And if I plug it in, what do I get? Okay, so df of pq is going to be the sum over y. Well, f of p over q is p over q. And that's going to cancel with this q and give me a p of y. And then I'll get the log of p over q. Does everyone agree with this? And that's actually something we've seen a little bit off and on. It's a KL divergence between P and Q, which is this well-known distance between distributions that's associated with Shannon entropy. And it turns out that the mutual information is the KL divergence between a joint distribution and a product of the marginal distributions. So this F divergence is actually giving us a mutual information if we apply it in that way. So I'll say when you apply this to a joint, to the joint distribution and the product of the marginals, you get Shannon mutual information. But you can also get others. Let me do one more example, which is just to have more than one, prove there's more than one F divergence. 1/2 absolute value of z minus 1. And that gives us an F divergence. Well, okay, I'll say the answer instead of going through the math. You'll get a 1/2 out front, and you'll get a sum over y of the absolute value p of y minus q of y. Yeah, basically you'll get that because you get absolute value of this minus 1, and then you'll multiply the q of y through. Okay, this has a name too. What's the name of this? Yeah, total variation distance between two distributions. Usually L1 is the same, but we take out the half, if I recall correctly. So you can get different well-known distributions as distances as special cases of F divergence. And I should have found and prepared this, but I believe it's true that the Dasgupta-Ghosh correlation could be written in this way, but I forgot to try to find the F that does it. But okay, so good thing to know about F divergence. And then when you apply it in the way we've been discussing, you can call this an F mutual information mechanism where we pay agents with the mutual information of their reports using one of these functions. Sounds good. It is good, but, and especially with time running low, I won't write the theorems from this paper. The challenge is still in estimating the F divergence with a finite number of samples in a way that can't be gamed. And I believe so some of these results need this large number of questions. So maybe you need sort of, yeah, maybe you have like an epsilon that goes to 0 in your results as the number of questions gets large. Or yeah, you might even need, for the theoretical results, you might say you need the number of tasks to go to infinity. I think for time, I will skip this though and try to get to determinate mutual information. Questions or anything to add?
So,
yeah.
Just to make sure, dominant truthful reporting, it means that truthful reporting is the dominant across all the equilibrium there is, or it means
yes,
reporting is the dominant.
Yeah, so that term came up somewhere, dominant truth, well, it's here even. I'm planning to write it up. Well, let me say it out loud. A mechanism is dominant truthful if, first of all, for all players I, being truthful maximizes your expected payment regardless of the strategies of others. Dominant strategy truthful. But then truthfulness is a dominant strategy of the game. Second, this is sort of the extra component they want. Truthfulness should pay strictly higher. So the truthful equilibrium, or if we're in the truthful equilibrium, okay, no, it's like when at least one other person is telling the truth, me being truthful should pay strictly higher than doing anything else. Actually, not quite that. We still have these permutation strategies that Jason mentioned back at the beginning, where we relabel the names of signals so that dog becomes I say cat and cat becomes I say dog. If we exclude permutation strategies, truthfulness should be strictly better than everything else. So that's really what we want to, that's the best we could hope to achieve. And so all these mechanisms couldn't quite get there until this one, which I'll summarize for you now. It's the idea that we've been talking about this entire second half of the lecture. We're going to use a mutual information between Alice's report and Bob's report to pay those two agents. This is going to be a mechanism that works with just two agents and some number of tasks, with relatively fewer assumptions on the information structure than we've seen so far. Now, what do we need? We need this mutual information to satisfy this data processing type inequality. What does it say? It says if we're truthful, so Alice is Alice's actual signal, Bob is Bob's actual signal, that has a higher mutual information, at least in expectation, than a case where, let's say, Bob is truthful, but Alice applies a strategy to her signal. And again, as Jason said, you can think of the strategy as what we would call a garbling. It's some randomized function of the signal, and it will always add noise if it's only a function of the signal relative to other information in the world like Bob.
But if this is true, then it is true also for even if Bob plays strategy.
Yes. So because mutual informations will be generally symmetric, this will also be true if
What I mean is the fact that
at the same time.
Bob is telling the truth or not, it doesn't.
Yes. Yeah.
It's true that
Yes. We kind of want this to be true more generally than what I said as well, and it is.
That's the dominant strategy part of it. It doesn't matter what Bob for any Bob.
Yeah. So right, instead of Bob here, I could have plugged in anything that's correlated with Alice.
it can be a
Yeah.
strategy of, it can be Alice strategy of Bob is higher than strategy of Bob and SA of Alice, for example.
Yes. So in particular, you could plug in Bob doing a strategy here, and this will still hold where Alice prefers to be truthful against any strategy of Bob. And intuitively, mutual information, even a strategy of Bob is providing bits of information to the mechanism. And the more information I give the mechanism, the more correlated I am with whatever it is Bob is doing. And the more my reward will be if I get this mutual information. But we need property 2. That's what we didn't have before this paper. We need this unbiased estimator. So I think I can, depends how much Jason wanted to say after this. I think we can write the mechanism on the board. Okay, the information structure is going to look basically the same as the one I wrote before, and so I won't rewrite it. There are many tasks. Each task is independent of the others, statistically independent. On each task, there's a joint distribution over the signals that agents could have. And we're going to do some a priori similar assumption and some consistent strategies assumption on the tasks. Okay. So, yeah, I'll just try to write the mechanism on the board rather than to finish rather than try to do it on the slides. Okay. So we assign each agent 2 C tasks, where C is this number that is going to have some importance for us. It's just the number of possible signal outcomes. For example, in the binary case, C is 2. Each agent observes, so agent I observes xit on task T, and they report, okay, now this notation is more standard, but I flipped the hat. They report XIT hat. And now here's the key idea. It's not intuitive at first, but there is cool intuition behind it. We're going to define matrices that are essentially the empirical counts that we were looking at before. Actually, there is a good slide for this. Let's go to the slide for that. Yeah, let's go straight to here. So we're going to split the tasks into two groups of size at least C each. Here's the first group. 1, 2, 3, 4, 5, 6 in this case, tasks. This is what Alice is reporting. This is what Bob is reporting. For this group, we're going to form this matrix, which is the empirical frequencies of pairs. So how often did both players report 0? How often did both players report 1? How often did Alice say 1 and Bob said 0? And the reverse. Okay. And we're going to take these matrices, and we're actually going to use the determinant of the matrices as a mutual information, which is kind of wild. So this is why we need 2 C tasks. We need C tasks in each grouping. I'll explain why. But the mechanism is to form those matrices. Let's call them M1 and M2. Let's ignore the UAs for the moment. And then the payment is just the determinant of M1 times the determinant of M2. And the claim is, okay, very briefly, but the theorem is that under these conditions, this mechanism is dominantly truthful. And this is on I believe two agents, because you have agent Alice scored against Bob, and you have Bob scored against Alice. So you only need 2 agents. You don't need many agents. And now just really quickly, as we're winding down, I'll explain I'll try to say why this is a mutual information, this determinant idea. Excuse me. Okay, so really briefly, there is an a priori matrix that is the probability of being in each cell, right? There's a probability, if we're truthful, that we're in cell 0, 0, a probability that we're in cell 0, 1, and so on. Let me call that U for the truthful matrix. Basically the DMI, we can define the DMI of Alice and Bob as the absolute value of the determinant of, did I call that U? That matrix U, where U is sort of a prior, it's a distribution of responses. Okay, now the claim that's not obvious is that this is a mutual information. But the reason is that one way to see it is that determinant kind of measures a volume of this sort of matrix as a mapping. And I think if you think about volume, it's a good intuition for this. And it turns out that if you garble these responses, so if you apply a strategy to the responses, indeed the determinant of this goes down, of this distribution. So the first key point, it's a mutual information. If you apply garblings, the determinant will go down. The second key point is that you need to not just worry about the a priori, the distribution, you need to worry about the empirical matrices. And there's a problem here, especially that first you have this absolute value. The key idea is that, well, I can also look at determinant squared. This is still going to be a mutual information. It'll still satisfy the properties of a mutual information. And I can estimate this by taking 2 different empirical response frequency taking the determinant of both of them and multiplying. So in expectation, I can take two unbiased estimators, basically roughly of U, take the determinant of each of them and multiply them. And in expectation, it will be the determinant squared. Now, it turns out the last thing I want to say about this technically, it's not as easy as that. It's kind of amazing, actually, because even though each entry is an unbiased estimator, the entries are correlated. And when you take the determinant, it's not at all clear that you should get an unbiased estimator. And in fact, you don't, you have to, but you almost do. And you just have to do some renormalization with some factor out front. And then it turns out to be true. So there's some magic going on in this proof that's really cool. But indeed, it all turns out to work out. OK, so let me stop there for determinant mutual information mechanism and ask for questions on that mechanism. And then we'll wrap up.
So you say that the determinant is basically mutual information?
It is, sorry, let me back up. There's Shannon mutual information, which we defined with the logs, Shannon entropy. Then we sort of said there's a concept of mutual information, and Jason talked about that, I believe, where basically data processing and inequality was the key component. And we talked about F mutual information as an example of that concept, as well as Shannon. But we couldn't quite find the right one. This is a better one for our purposes than those, because we can do this.
So my question is, so this measure, I don't quite understand why we need to take the square, like if the det M1 is already an unbiased estimator.
Yes, the problem is the absolute value here. This is an absolute value sign. So we can unbiasedly estimate the determinant, but we want to pay you more as the absolute value grows. And we'll use the square to do it. Yeah. Yes.
Can we do anything if we have like continuous no outcomes? Or like can we do something
I don't know. Maybe, do you guys know if they're like continuous outcomes or real valued outcomes? I think it's going to be a problem. One thing that happens with this is if you have very sparse matrices, you're in trouble because the determinant will be 0. Like, if you have a matrix with a 0 determinant, it's quite likely if you don't have very many tasks compared to the number of cells of your matrix that you get something with determinant 0. And only once in a while do you get a non-zero determinant. So increasing the number of outcomes is a problem. Yeah, you need to ask many, many more questions. OK, we're over time. So maybe, should we probably take it into lunch and the break from here on out? What would you say? OK, quick one. So
repeat the same tasks twice?
You don't repeat. You have many tasks, and you group them into 2 groups.
But are those the same task? Group 1 and group 2, are those the same tasks?
No, these are all different tasks.
But then, how you can be sure that the agreements...
Let's discuss it up here right after we...
The rows are the same task.
Sorry, these two, this is the same task, this is one task, this is one task.
No. You replicate in the second group the same task.
Nope, different, all different. So this is an independent random variable from this one.
But sometimes you like McDonald's and the other one...
Yeah, let's discuss it in the break. So do you have anything in closing that you wanted to say before we...
Is there anything on the slides? I don't think there is.
I don't think we had like a big wrap up slide. So let me just do a real quick recap. Yeah, is there? Oh, there might be a good references or. Yeah, so we have a lot more that you could read, and you'll get these slides, or if you haven't yet, or you will later, I think. Lots more references. But is that?
Thank you.
Other models, empirical work, experimental work. Yeah, these are just like other directions you can take this.
Yeah. So this literature is actually really huge. A lot to explore. We can try to discuss The recitation leaders can discuss with you. And yeah, so that's it for peer prediction. Thanks.